So weeknight's pretty simple. Basically, it talks about supply chain strategies. We've talked about all these different pieces like VMI, third-party logistics, things like that. Now we're going to look at how they fit into an overall strategy. And the lecture notes, I think, do a pretty good job of this. They talk about Dell when they talk about push-pull. And it's a pretty good example. They talk about Amazon with their 3PL, I think. So, and then they give you a couple other examples of things that we've talked about previously in the class, so I didn't go in depth with this week. But I'm basically going to cover two things this week, push-pull production and retailer-supplier partnerships. Then at the end, I'm going to briefly go over theory of constraints, give you an idea of what theory of constraints is, and also I'm going to contrast between theory of constraints and lean really quick. So like I said, sometimes you hear people put lean and theory of constraints in the same bucket, and although there's a lot of similarities between the two, the way that they accomplish their tasks are completely different, and that's very important. You'll see. I won't ruin it for you. So push-pull production. I like to use this because I think this really epitomizes why push-pull is really good. So let's say that you own a seafood restaurant and you specialize in having fresh seafood every night, and you always pride yourself on having a catch of the day and a very robust menu. So if you were going to create a seafood restaurant, which strategy do you think would work best, push or pull?
Probably pull.
Okay. Pull would work, and in a way, I guess push would work. So when we look at pull versus push, okay, the pull is great because we can reduce costs because you have less stuff in your system because you only pull stuff out as required. But unfortunately, when you reduce costs by having less stuff in the system, your reduced work in process and your inventory restricts your ability to react to high variations. So if your forecast is for five items per month, and all of a sudden there's a sudden request for 6 or 7 or 8 or 10, that puts a huge demand on your suppliers to suddenly ramp up. And because we deal with such short lead times, they have to ramp up their output in a very short time. Okay, so, and some companies can do it. Some companies specialize in having all this excessive capacity so that they can do that with certain products. Obviously, like I tell people, you can't put 9 women in a room and get a baby in a month. You have some constraints, unfortunately.
That's a great example.
Thanks.
Does the length of the supply chain have anything to do with that work in progress and inventory? Because I'm thinking, like, let's say take a sushi restaurant in Tokyo. They got the Tokyo Fish Market right there, so they can just immediately go back and pull as needed.
Right. You're absolutely right. This is where the push-pull comes into play, and you'll see that in a minute. You're right. Push really needs very small lead times because of that, because you need to be able to react quickly to variations. Now, of course, you can use safety stocks or what they call buffer stocks, as you may have heard in theory of constraints, to minimize the impacts of sudden variations in demand. But overall, a lean system or a pull system really relies on having low lead times and fast demand. Well, I guess lead time, the demand signal is part of the lead time. If it takes you 3 days to tell your supplier that you need to build something, you have to add that into your lead time, obviously. So overall, you want really short lead times, because if you don't, you become very vulnerable when you have variation. Okay, and that's where a push system has an advantage. If you have a very high variation or you have a very undisciplined supply chain, you might want to go push because, yeah, you'll suffer from excess inventory or the risk of excess inventory, but at least that vulnerability of having low inventory in your supply chain is kind of mitigated. Does that make sense? So pull systems also use reduced cycle times with predictable outputs. So basically, if you're able to create a robust pull system, you reduce the time it takes to make something. So when the customer says, hey, I want blue instead of black, your ability to give them something that's blue is much quicker in a pull system than with a push system where you say, oh, well, we have to stage a whole bunch of blue stuff. And if you don't have any more blue stuff, well, hey, like Henry Ford said, you can have any kind of car as long as it's black. Which is something about variation in a system. Ashby's first law of systems says only variation can absorb more variation. And this is where this comes into play. If you're going to want to absorb variation in your supply chain, you need to be able to have a system that can absorb the variation. So if a person says, I want blue, you have to design the flexibility in your system so that they can react to the new request. That makes sense? So now, flexibility, obviously, as I just mentioned, pull systems allow products in a supply chain only when needed. So when the guy wants the blue one, it'll only pull the stuff that is required to make a blue product. But unfortunately, like I said earlier, you got to have very accurate forecasting or just-in-time demand reporting. So pull has strengths and weaknesses, obviously. So let's say that we did our seafood restaurant as a push restaurant. So we push products into our restaurant, but suddenly we would have a lot of inventory. And if we pride ourselves on having fresh food, obviously you can't hold a lot of inventory before you have things like spoilage. So obviously a push strategy may not be the best for something like a seafood restaurant because you won't have things will happen too quick. Things happen too quickly for you to be able to pull inventory because the thing about a push system is that we work to a forecast and we ship things out to meet a certain forecast set of sales. So lead time isn't as sensitive in a push system. So if your lead time, if your customer orders a grilled fish sandwich and he's willing to wait 4 or 5 days, that's great. You can call up the fisherman and he goes out there and gets that fish and everything else. But if he wants a sandwich right now, the push, obviously, it's not really good at getting things fresh, obviously. So push systems do not need just-in-time customer demand because they work on forecasting. But as we noticed last week with the bullwhip effect, you can have oscillations when you have variation in your demand forecasting, or if you have variations in your actual demand also. Okay, I don't know if you had a chance to play with that website where you put in the various variables. It's actually fun to do because you really see how like such small changes in demand cause huge oscillations where suddenly you go from like 25 extra to like now you're down 2 or so. That's a huge weakness of a push system. So, and as we know, push systems cannot react to immediate changes. So going back to your seafood restaurant, if you had a customer who suddenly changed his mind about an order, you're really limited by your inventory on hand as to how much you can react to a customer's immediate change in order. Okay. So let's go quickly back to a pull. If we design a seafood restaurant as a pull restaurant, basically you pull the fish out of the ocean just in time or with low lead time. So in this example, if a customer orders a fish sandwich, as soon as he orders a fish sandwich, you basically tell the fisherman, hey, pull that fish out of the ocean at this time. Okay. And then at the same time, that he'll have to pull out of the ocean the exact fish that you're looking for. Well, obviously, that's a weakness of pull. if your supply chain isn't able to give you just-in-time supplies, your pull system is going to fall apart. I think in like week 2 or 3, I talked about how Boeing really pushed suppliers to give just-in-time to them. And you had a lot of suppliers who didn't have a pull-compatible manufacturing system. They needed to have a lead time. And as a result, Boeing said, well, then you're going to have to take on the inventories on your payroll because we're not going to pay for it. We're only going to pull stuff when we need it. And a lot of suppliers got in trouble because they said, well, we don't want to absorb this extra cost. So all of a sudden, Boeing started to have shortages because you had your suppliers with a push mentality and Boeing with a pull mentality. And it's like, well, crap, this doesn't work. It doesn't work because the people needed extra time, extra lead time to get things out. Does that make sense? Okay.
Yeah.
Great. So now, use the pull system for a seafood restaurant would require, like I mentioned earlier, fish to be pulled from the ocean and made available to the chef immediately. And he has to have any type of fish available that must be caught at the time of demand. And only the needed amount of fish. So if you get an order for 4 sea bass and 3 tunas, that's all he's going to pull out of the ocean. Anything above that is waste. Or anything below that, someone's not going to get their sandwich. So, and the customer demand must be made immediately known to the fisherman. So, which wouldn't be that hard. You can give the fisherman a cell phone, but his ability to pull the exact fish out of the ocean is kind of hard, obviously. But if we use a push system, you have the same problem. Well, it's the same types of problems. The fisherman would start to stock extra fish in anticipation of what you're going to do. But fish being the way they are, you may not want to have a lot of fish on your ship at one time. It's probably not sanitary.
In this example, he may pull them out of the ocean, but put them in a fish tank on his, in his whatever facility or on the boat, waiting to be sent to the restaurant.
Yeah.
But then with the second bullet, this potential for spoilage exists because he's got,
and let's say no, you're right. Let's say for some reason you asked for 3 sea bass and he just can't get sea bass out of the ocean. He's like, I've been trying like crazy. His suppliers didn't give him the kind of stuff that he needs to provide you with your products. So obviously a push system has a little bit of flaw. And of course, you have the potential for shortages and high movement catch of the day products. We talked about a few weeks ago between cheetahs and elephants and cheetahs, zebras, and elephants. If you have something that's an elephant, something that moves very, very slow, and all of a sudden it becomes the thing, the catch of the day, your elephant becomes a cheetah. Well, your suppliers have to be able to change their system to match your sudden cheetah, your high demand. So obviously you have the potential for shortages. So does that make sense? Awesome. So now, this is where the push-pull strategy comes in. The way that a push-pull strategy works is we're going to use a push strategy to a certain point. Okay. For instance, you talked about the Tsukiji fish market in Japan where they have all the tuna and all the fish available.
Right, they're the staging area.
Yes, that's a staging area. And what the restaurant owner will do is just say, okay, well, what kind of fresh fish is available at the market? And then he'll set his menu based upon what's at the market. Okay. So in the case of Dell, what Dell does is Dell says, okay, do you remember the theory of postponement where you modularize and make common components as far up the as far up the supply chain as possible?
Yes.
Okay, that's a way to speed up your supply chain. Well, Dell does that. Dell uses a push strategy where they modularize or have common components as far up as they can until they have a point where the customer basically builds their own computer. But when you look at Dell, all the stuff that a customer customizes is all common products. It's so Dell modularizes or standardizes parts all the way up to the point where they're assembled. Then when the customer says, hey, I want this blue computer, Dell has everything available to make a blue computer. At that point, it's a pull system where Dell waits until the demand occurs. They have all these parts that have been pushed to the staging area. Then they build it. Then they send it off to the customer. Does that make sense?
Yeah.
Okay. So this is a push-pull strategy within the confines of a seafood restaurant would work great, because you say, hey, fisherman, get me the fish that you're able to get. I'll create a menu based upon what you can give me. And a lot of seafood restaurants do this, especially like ones near water. They'll say, well, the catch of the day is something that some fisherman made available. So it's a pretty, and this is something that I believe came from Japan. I think Toyota came out with this first, but Dell has taken it and in some ways has improved it. So that's the concept of a push-pull strategy. Any questions? Okay. Pretty easy. All right. So now retailer-supplier partnerships. If you remember a couple weeks ago, we talked about sequential supply chains. And this is one in which the supplier assumes a risk of excessive inventory from units that haven't been ordered by the buyer. The buyer assumes a risk of excessive inventory from stuff they can't sell. So as a result, the buyer will only buy stuff from the supplier up to the level of demand. And the supplier will only make as much as is ordered from the buyer. So as a result, you sub-optimize the system. Okay. So as I said here, each side is polarized with the fear of imperfect information. And what also happens, as several people noted in the class, there's mistrust. Because let's say that the buyer wants to get more units. Well, they may inflate the demand forecast, but the supplier, and the buyer, based upon their strength in the relationship, may say, well, we may have an inflated demand forecast, but we may put it in the contract where you have to only give us so many items, and the rest you have to put in inventory. I've seen that quite a bit. Or the supplier, if the supplier has the strength, they'll say, hey, look, you need to guarantee us X number of products every month, or else we're going to charge you more. So they force the buyer into buying products that they may not be able to sell. That happens quite a bit. And of course, these are not really good relationships. So what we do now is basically have a partnership in which the retailer shares their demand forecasting information with the suppliers. And at that point, the retailers and the suppliers sit down to determine the best levels based on demand forecasting. This is very similar to last week when we were talking about the like some of the make-to-stock and make-to-order contracts. Okay? So this is kind of like VMI also, but whereas a VMI is where the retailer controls the entire chain, this is where the retailer works directly with the manufacturer. So in this case, there's an example in the book where they talk about Ryder, I think, does this, where they as a distributor works with the retailer and the supplier to share demand information and set manufacturing levels. Now, my experience with these is that they're still vulnerable to relationships. Like, for instance, if the retailer has a strong relationship compared to the manufacturer, they will generally force the manufacturer to keep stock to buffer against demands. So they'll say, yeah, we will share our demand information, but you will be obligated through a contract to provide so much product within so much time. So it kind of forces the manufacturer to take on some of the risk in this relationship. And vice versa, I've seen where suppliers with smaller retailers will not give them preferential shipping. They'll say, hey, look, we will work with your demand forecasting, but just realize that unless you give us a premium on our manufacturing costs, we have the right to send our stuff to other people first. So they actually force retailers either pay them more or to take on some of the inventory costs. So
they create competition among the different retailers for the same product.
Correct. And I was reading some research where there was like 2 or 3 papers that I read earlier where they're saying that trust is a major issue in these because the retailers go, okay, yeah, I'm going to share my demand forecasting, but now the manufacturer has an advantage because now he or she, they are able to now you use that against you. They'll say, hey, look, you have a high demand coming up, so we know you're going to be willing to pay a little bit more money to have stuff shipped earlier. So now they can do things as a manufacturer to force the retailer to make certain decisions. And
there was an example in the book of that information sharing got the guy was sharing information with the manufacturer and it got to one of his competitors and it kind of screwed him in the end. That was in.
Oh, sure, yeah. So, yeah, I've seen that personally where I was in a program where we took one supplier's information, gave it to another, said, hey, look, this supplier is willing to offer us this. What can you do for us? It's like, wow, not really ethical. But, yeah, unfortunately, what's ethical and what's legal are 2 different things. So, yeah, but that happens quite a bit, unfortunately. So, as a lot of the people in class kind of came up and said, yeah, it sounds good on paper, but you're still vulnerable to human nature, unfortunately. So, so this is similar to some of the make to stock and make to order incentives. And although it sounds great on paper, like I said, more often than not, it ends up in a tit for tat type relationship. Rarely have I seen a true collaborative. But the best I've seen is like Toyota. But Toyota really comes up and says, hey, you will collaborate with us and we will share things with you. And we will be open with you and you'll be open with us. And if you're not, we're going to drop it like a hot rock. But Toyota has the ability to force collaboration like that. Other companies.
They have interior lines for their supply chain versus exterior lines.
Exactly. Yeah, and I remember working with a few people who worked with Toyota in Los Angeles. I got to meet a few of them when I worked there. And they said, yeah, when you become a supplier for Toyota, they go to your place and basically create, they turn you into a lean manufacturer. They bring in experts and they invest in you and everything else. So people like stand in line to become a Toyota supplier, but when that happens, Toyota is like, okay, we've invested in you. Now we are partners and you will act like a partner.
That kind of goes with what we read this week in the reading where Toyota's kind of trying to design the supply chain so it all meets the same goals.
You're absolutely right. And they kind of went away from that a little bit when they had their quality problems. And I actually wrote a paper when I was doing my PhD on this where Toyota's leadership passed hands to the younger quote unquote generation who was all about profit maximization. So they began to reduce lead times with test trials and stuff, and as a result the quality began to go lower and they started to push all these demands on the retailers and started acting like they, started going away from their model. And as a result, all these quality problems came up. So the old man came back in the company and said, hey, look, yeah, we screwed up, but you know what? We're going to fix this. So even Toyota strayed away from it. And then, but they, as we know, they had their huge quality issues. So now they've kind of come back to their old strategy. So as I said, this is a good partnership if you can get it to work. Unfortunately, it really requires a lot of trust on both sides, and in most business scenarios, that trust isn't. The two things of research said that when they're both equally sized, the collaboration is really good. But when one is bigger than the other one, there's a tendency for the bigger one to push the smaller one around. So. All right, so any questions? Relatively straightforward. Now, theory of constraints. I know I talk a lot about theory of constraints because it's a really good tool used to improve the performance of a supply chain by identifying constraints and reducing or eliminating them. And as I mentioned before, these are frequently applied in conjunction with other systems-based practices like TQM, Lean, and Just-in-Time. Lean and Just-in-Time are very similar. As a matter of fact, I was reading something earlier where it's like Just-in-Time, like Lean. Like Just-in-Time is a subset of Lean. You can have a Lean supply chain, but not necessarily a Just-in-Time supply chain. So, but it really works well with Lean. The difference between Lean and theory of constraints is that although they both focus on improving the flow of products to the system, they do it in two different ways. Lean focuses on identifying waste in the system and either eliminating it, or if it's something that's acceptable, you try to mitigate it. Like there's some waste that you just can't work without. Okay. Whereas theory of constraints deals with identifying constraints. We don't try to eliminate waste. We try to reduce constraints, and it's a subtle difference because in theory of constraints we realize that you may have waste, but if the waste isn't in a constraint that reduces your flow, we're not going to deal with it. We're going to go to the place in the system that impacts our flow, and we'll deal with constraint there. We may reduce waste there, but we're not going to focus on waste in a non-constraint area. Whereas in waste, you would look at the waste everywhere in a lean system. So does that make sense? Okay. So, the theory of constraints has this thing called 5 focusing steps, and this is how the theory of constraints system focuses on eliminating constraints, or how it focuses on improving the flow within the system. So what we do within the theory of constraints system is we look for a constraint that's slowing down the flow within the system, and there's various tools. I'm not going to go through it now. It's that itself can be a whole class. So we go through, identify a constraint. At that point, we decide how to exploit it. We exploit the constraint by reducing the constraint's impact on the flow, such that the impact is below so that the time of the constraint on the flow is less than other parts of the system, so that the overall system flow is improved. I'm going to show that in a minute. So once we do that, we subordinate everything else to the above decision. Every decision is focused on removing that constraint. Then once we do that, we elevate the system's constraints. And if the previous steps, a constraint has been broken, go back to step 1. So once that happens, we elevate the system's constraints. We look for the next constraint. And if the constraint moves somewhere else, we apply this to the next constraint. So it's a constant loop of looking for constraints. You exploit the constraint, subordinate everything else to that constraint. And I'm going to show you that in a minute when we talk about drum buffer rope. And then once that's done, we elevate the system's constraints, look for the next constraint in line. And then once you do that, we do it again. So much like lean, you're always doing the whole muda, looking for waste. This also does the same thing. So it's a continuous improvement process, much like TQM and other things. Now, drum buffer and rope. This is pretty basic, but is actually a very powerful tool in removing a constraint. So you have two things. You have the drum, which is the pulse of the system, and I'll explain that in the next diagram. You have a buffer which is used to slow down certain parts of the system. If a certain part of the system is going too fast, you want to smooth out your flow. And then you have a rope, which is used to pull. You go to the constraint that has the longest time impact on the system, and you use that to pull products into your supply chain. And I'm going to use and here's a simple diagram. We have 5 processes, or you can say 5 steps in your supply chain. And if we look at this, the amount of time it takes to get one product through your system is always going to be the process or the step with the longest time. So in this case, no matter how much stuff you put through the system, you only get one product out once every 6 hours. Okay? So we place a buffer, like any kind of buffer, between 5 and 6. Basically, say we're going to improve your process C by maybe adding more resources. So we're going to try to mitigate process C here. The time buffer is placed here because we say, well, look, this guy's only going to be sitting here for 2 hours and he's finished with his process. So he's going to be waiting for 4 hours before process C can give him something. So we're going to put a time buffer here and say, hey, look, wait 4 hours. Okay. The drum is the speed of the system. So if the process is at 6 hours, basically everyone is only going to go the speed of 6 hours. Okay. So obviously there'll be some delays here. So our goal is to mitigate process C, and this is where this buffer comes in, where we are trying to either add a buffer stock or whatever to process C, to reduce process C's time from 6 hours to whatever. Okay. And this rope is basically telling us that every 6 hours, process C is going to pull on the rope to allow the next thing in the system. This eliminates shoot, I just had a brain fart, sorry. This illuminates work in process. This eliminates having stuff pile up at process A. Okay. So now, if we're able to get process C down to 3 hours, what is the pulse of the system here? What would it be?
Process B. Process B.
Be 5 hours, exactly. So what they're saying is, hey, look, you will only get as much improvement as the second worst process. So you can go from 6 to 3, but just realize that you're not going to get double the improvement in your system. Okay? And this is where I've seen many times managers, even not in theory of constraints, but in processes in general, they'll go, well, yeah, I reduced process C by 50%, so I've improved the system by 50%. It's like, no, you haven't. You've only improved it by 1/6. So now you got to go to the next process. So in a theory of constraint system, you would work on process C. You would add a like a buffer stock where I have the money there. You would add a time buffer, basically telling process D to wait 4 hours before you start the next process. And then your drum would basically be your pulse, tact, same thing. And your rope, which basically is the demand of the system, is going to be every 6 hours. Now, once you fix process C, you go to process B, and you can do the exact same thing. At that time, your rope is going to be 5 hours, okay? And you may put something else over at before process 5, some kind of buffer to improve the flow between process A and process B. But note that when you do that, the constraints will jump around. Like sometimes if you fix process C, some of the other processes may end up taking longer all of a sudden. And that's just, there's a term, I think it's called like jumping constraints or something like that. So this is a continual process where once you change something, you check the entire system to see what, where your new constraint is. Okay. Does that make sense?
Yeah.
Okay. It's a pretty straightforward system, and it's actually very simple. Theory of constraints has a lot of tools for how you take care of all of these things, but basically drum buffer rope is the synopsis of what all the tools do. You either focus on the speed of products going through the system, which is the drum. You focus on putting buffers around to improve the flow, or you work on slowing down the amount of parts coming into your system so that you reduce work in progress and parts piling up in processes. Okay? Because what I've seen a lot is like, let's say, the guy at process A, he's putting them out every 3 hours, and process B, he may after a while, he may have like 4 or 5 parts sitting on his bench. And they go, well, heck, process B, you're being lazy. We'll reward process A because he's being really fast, and we'll punish process B because he's really, really slow. But the constraints, process B may have constraints that he has no choice over. When actually process A is costing the company money by increasing the inventory within the system. Actually, process A should be punished because he's actually wasting money by having too much stuff built that can't be pushed through the system.
So if I could give you a practical example, and you can tell me if I'm tracking correctly this theory of constraints.
Uh-huh.
So process C, let's say it's a fulfillment center and they have like 37 different kinds of product in this massive warehouse. A buffer, and the problem that they're having is it takes 6 hours to pick all of the stuff that has to go onto the trucks in process D and to be loaded. So a buffer is, let's say they had only 4 pickers to get the product, and the buffer is they add 8 pickers to the process. So now process C is cut down
to 3 hours, we'll say.
To 3 hours, yeah. Is that correct?
Yeah.
And then process D was the process of loading the trucks, so they slow it down a little bit. Instead of having them come in at 8 a.m. to start their shift, now they're coming in at 10 a.m. to start their shift.
Sure.
Or 11 a.m.
Or you have the guys at process D do something else.
Yeah.
What you could do is have the guys at process D, hey, why don't you guys help out process C for 4 hours?
Right.
Then shift back to process D. That's a TQM thing where TQM is all about cross-training, so that if, in this example, process D is sitting around for 4 hours waiting for process D can go over there and help out process C.
But if you're focused on cutting costs, instead of having them stand around for 4 hours, you could have them come in 4 hours later, so that
sure,
by the time they come in, they're ready to handle process C's work.
Sure. Yeah. Yeah, like in your example, the fulfillment center of process C could be 20 miles away from process D, which could be a local retailer. Yeah, it's gonna be hard for the retailer to help out, the fulfillment center that way. But you can say, hey, look, we're going to slow down the demand on the system because, there's always this knee-jerk reaction. We got to whip the system harder, but systems don't work that way. If you try to make this system so that process C just goes faster because you're whipping them, you may get temporary improvement, but eventually the system's going to break down. Either the guys are going to suffer from burnout, equipment's going to break down, you may have quality flaws in your production, whatever. So they say, look, realize that this system it can only send parts out once every 6 hours. And what you do in this case is you basically either you slow down the customer demand, say, hey, look, dude, you can order it now, but you're only going to get it 6 hours from now. We can't help it. Or you put in put in buffer stocks to improve it, obviously. But it's folly, and I've seen it many times in my industry where we'll beat on a supplier to get things out quicker, and all of a sudden we have all these quality problems. Just because their system isn't set up to be able to produce faster than the speed of the system. That's why in the system it says, look, we're going to slow down everything to the speed of the slowest process, because that's the most sustainable speed that parts can go through it. So yeah, so it's a pretty straightforward concept. I love it. I love Lean also, because Lean's got a lot of really good tools for cutting down waste and everything else. They both work very well together. But just as long as you remember that they both try to accomplish the same thing, but in different ways. That's the main thing to remember. Okay? All right. Well, that's all I had, because the rest of it is pretty much for this week. It's pretty much stuff that we've gone over in previous weeks. Whoops, there we go. And so I didn't go through like VMI or third-party logistics again, because I think we pretty much beat that horse pretty badly in the last few weeks. But I think the discussion questions talk about supplier-retailer relationships. The handout does a pretty good job of it. The book has a pretty good section on that also, so hopefully there won't be any problems.